Hey, man, I asked them to leave the classroom now. Recording and talking don't go well together. Good afternoon, everybody. Online, can you hear me? Can you see the screen?
Yes, sir.
So no, don't get me upset. I don't sound very nice when I'm upset. All right. All right, guys. So what we're gonna do today? We're gonna work through this last question. All right. So well, two questions here. This one, transformation. I'm gonna do these vectors down here. We did this one as a classwork the other day. So we're gonna do this one down here. And then we're gonna try and see if we can do as many of the questions on the paper that I sent you the other day. All right. We don't finish all of them. What I'll do, I'll send you another paper. And we're gonna do some of that one, finish those, and then do some of the other paper that I'm gonna send you. More maths equals better maths every time. All right. So let's start with this transformation on this sheet up here. Matrices and transformation. All right. And then what I'll do from the paper that I sent you yesterday, I'll work from the back to the front. I'll work from the back to the front. And I'll send another paper for you to practice from as well. We're gonna keep practicing right through the holiday until we start with the trigonometry, continue with trigonometry in January. All right. So you have class Saturday as usual online. All right. So this question part A. This question part A gives us this, mute the mic please, online. Gives us that matrix M and it tells us that we have to show that it is singular. Show that it is singular. Another thing they could have said is show that it has no inverse. They could have said that as well. If it is singular, it has no inverse because the determinant is equal to 0. So to show that it is singular, we need to show that the determinant is equal to 0. All right, that's all we have to do. All right, so here it is singular, which means it has no inverse. And the determinant is equal to 0. All right, so we just need to calculate the determinant of M and it should come out to be 0. So the determinant, hold on a second. The determinant of M is equal to this product across here. That's a negative 6 times 60 times 10, sorry, negative 6 times 10 minus this product across here, which is 5 times negative 12. So this becomes a negative 60. And this negative 5 times this negative 12 becomes a positive 60, which becomes 0. That's what you have to show. Therefore, M is singular. Show that determinant is 0 because the determinant is 0. That's the reason why it is singular and has no inverse. All right. Another way they could have also given you a question to say, show that the matrix is non-singular. So in that case, you would work out the determinant just the same. Work out the determinant just the same. And the answer would not be 0. You get a value that is not 0. That would mean that it is non-singular. All right. So basically that is that. Easy as that. So it's like 3 marks, but believe me, some people don't know what to do, but that's what you do. All right. Work out the determinant and show that it is 0. And this one says we are to calculate the value for A and B. I said it's in gone. Let me see. Calculate the value for A and B on that equation. So that's an equality of matrices equation. Let's zoom up on it. All that this thing means is that this 8 is obtained by multiplying this row by this column. So we can set it up. The 2, 1 row times the 5b column is equal to 8. So then this first element times this first element plus this second element times this second element add to 8. So 2 times 5 is 10 plus 1 times b is b. That is equal to 8. Subtract that 10, the b becomes negative 2. And then now, to get the a, what it is that this 7 is equal to this second row times this one column. And so we can set that up again. The A4 row times the 5B column, but we know the B, we know the B is negative 2, So we can, in fact, put the negative 2 here. That now is equal to the 7. Just put in the negative 2. So the A4 times the 5 negative 2, because we know that the B is now negative 2, is equal to 7. So then this first value times this first value, first element times first element, plus second element times second element, add to 8. So it's 8 times 5, which is 5a, plus 4 times negative 2, that's negative 8. So we can just say minus 8. That is equal to 7. Transpose this 8 and add it, we get 5a equals 15. Divide by this 5, the a is equal to 3. That is it. What go to that? But okay? Nice and easy. Equality of matrices. All right? Equality of matrices. I'm recording the session. If you never know before what to do, you go and watch about the video and do it by yourself. And about the foolishness. All right. Next question. These are all stuff that we know, just applying an application of what you already know. All right? The question not going to come straight, same way all the time. Questions will be set to test your knowledge. And you have to apply your knowledge. All right. This one now is a transformation. Part C. It says a geometric transformation S, it maps this point onto that point. And they said that S is this matrix. How does the matrix work? The matrix multiplied by that point is equal to that point. So you're setting up an equation again. It becomes like another equality of matrices. It becomes something similar to this. So let's set it up. When you apply the matrix S to the point E, the answer is E prime. E prime. You apply the transformation S to the point E, the result is E prime. So the matrix will tell us is 0x, y is 0. Multiplied by the column vector for E. E is this point, 5, 2. That's like the position vector. Know that we're doing vectors. We know that this is actually the position vector. So we're working with the position vectors. Is equal to the position vector for E prime, which is 2, negative 5. So it's similar to what we just did a while ago. It's an equality of matrices. All right? Let me use a different color. This 2 is equal to this row, or it's obtained by multiplying that row by that column. So you set up the equation like that, and the equality of matrices. Set up the multiplication like that. So the 0x times the 5, 2 results in this 2 over here. And you work it out. So 0 times the 5 is 0 plus the x times 2 is 2x. That is equal to 2. So if 2x equals 2, then the x is equal to 1. And then this negative 5, now we're going to work out for that negative 5. This negative 5 is obtained by multiplying this row by this column. Same thing again. You can set it up, or you can just do it, but let's set it up. So the y is 0 times the column 5, 2 is equal to the negative 5 under here. So you multiply them. First element times first element, second element times second element. So it's y times 5 is 5y. 0 times 2 is 0. That's all equal to negative 5. So if 5y equals negative 5, because the 0 becomes immaterial, then the y equals negative 1. And so the matrix S, let's put it in blue now, the matrix S is equal to 0 and this one, because the x is 1. And then negative 1, 0. And then you want to be at a level where by just looking at that matrix, you know what transformation it is. That's the level you want to be at. Know the matrices to that level. That's a rotation matrix. 90 degrees clockwise about the origin. But the negative is 1 is down here. You have to learn the matrices like that. Like you see somebody name, I know it. That's how you want to know the matrices on site. But the question is easy. The more things you know, the better at all times. The more things you know, the better. As much of the things that you can know is the better. All the things that they set in questions, all the things that the questions are centered around, it makes sense to just know those things. Questions become easy, easy, easy. So if they ask you to describe it or whatever, at least you know what you're working with. You're working with the 90-degree clockwise rotation about the origin. They ask you to describe it, you're good. Anything they ask you, you're good, because you know what it is. You're not working blindly. All right. That's the first part. The second part says transformation T maps this point onto G prime. And I want us to work out what G prime is. How transformation works, you're adding the translation or translation. How translation works, you add the translation matrix to the point, or to the vector for the point. So it works like this. So the G plus the translation equals G prime. That is how translation works. It's the only one that you're adding the translation. The 2 by 2 transformations, you multiply them. Translation 1, you add it. Because like you're moving the point using the translation matrix. So the matrix for G is what they gave us here. They gave us this point, so it has the same values. It basically the position vector of the point. Know that we have done vectors. So it is 7, 1 is a column vector for this point. Plus the translation matrix is this, negative 3, 4. That's going to give you the G prime. So you can work out the G prime. So it's 7 and minus 3. 7 minus 3 is 4. 1 and 4 is 5. So this is the position vector for G prime. What did they ask for? They asked for the coordinates of G prime. You don't give coordinates like that. That is position vector. You write coordinates like this. You say, therefore, G prime is 4, 5 with the same values. You should appreciate this a lot more now that we have done the topic of vectors. So these are really the position vector of the point. That's what it is. This is the position vector of this point. So this is the answer right here, not this. Very good? Beautiful. Then it says now, under the same transformation, H, which is that point, I don't know the value, PQ, is mapped onto this. Under the same transformation G, the translation G. They want us to work out these values. So you can set it up again. It means that H plus T is equal to H prime. This question have so many questions centered on equality of matrices. So you set it up. The H position vector based on this being H would be PQ. Plus the translation with the same translation, minus 3, 4. That results in H prime, but you know the values on H prime, 2, 6. And you want to find what these are. Easy. If you want to find P, you transpose the negative 3 over there. You want to find Q, you transpose the 4 over there. Or you can take this vector over there and subtract it to find this one, PQ. So you can say PQ comes equal to 2, 6 minus the minus 3, 4. What we have really done is apply the inverse of the translation. You could have thought of it that way as well. You apply the inverse of the translation. Because if the translation takes you from H to H prime, then the inverse will take it from H prime back to H. The inverse of a translation is the negative translation. That is it. But you can just do it like this as well. So PQ becomes equal to 2 minus gives us a plus. That is 5. 2 plus 3 is 5. And then 6 minus 4 is 2. The question asks for the value of P and Q. So you can't give them that as the answer. You know? You have to tell them what P is and tell them what Q is. Answer the question. So you can't leave that as the answer. You have to now say, therefore, the P is 5 and the Q is 2. The P is 5 and the Q is 2. And present this as your answer. Question asks for the value of P and the value of Q. You have to state them explicitly. You can't just have them in the matrix and leave that as the answer. Very good at that? Very good. Then down here now, it says, obtain. Interesting that this question didn't ask us to describe a transformation, but that's fine. Some question would. To be a clockwise 90 rotation about origin. Down here now, it says, obtain the image of this point under the combined transformation S followed by T. Remember, because a translation is involved, you cannot do it in a single step. You cannot do it in a single step. S followed by T would have been represented by TS. That's how you represent S followed by T. Right? TS. That's a representation for S followed by T. So instead of saying transformation S followed by T, they could have said by transformation TS. And you have to know that TS means S followed by T. Right? But because that translation is involved, we're going to do it step by step. We're going to do the S first and then do the T afterwards. All right? And look here. We don't have to do no calculation really, you know. The same way how the S change the values on the E is change the values on this one the same way. What did it do? It switched around the values. So the second value goes to the front and the first value goes to the back and change sign. You can just do the same thing with these points. You don't need to calculate it. And they add the translation. All right? But you can calculate it too. So this is what would happen. So we take the point P, multiply it by S, right? As S followed by T. That will give you a result, and you would add the T to get the answer. Right? Let's call it P prime. So you apply the S first to the point P, and you apply the translation afterwards. Whatever this works out to is the answer. So see here, the S was 0, 1 minus 1, 0. Apply that to the point P. P is 10, 12. That's going to work out the S first. You know? And after this works out the S, you're going to add the translation. And the translation was this one over here. Minus 3, 4. That is your P prime. We're just going to complete this now. What does this do? So you can, if you want, you can just do the 0 times that is 0. The 1 times 12 is 12. So this works out to be at 12. Then the negative 1 times the 10 makes this a negative 10. And you're adding the translation minus 3, 4. That is what is giving me my P prime. Then I complete this. 12 minus 3 is 9. Minus 10 and 4 is negative 6. That is my P prime. Question asks us for the coordinates. And so we're going to write, therefore, P prime has coordinates 9, negative 6. That is it. But I go to that. If you want to go step by step, go apply the S first and work out this point, you know. Then after I get this point, they do the translation. But I'm just combining everything. It's combining everything. Do the S and the P first. See what that will be, and then add the translation. I'll do it S followed by T. But good. Suppose them say T followed by S. Suppose them say T followed by S. If they said T followed by S, if it was T followed by S, means that you have to do translation first. So how that would go, you would have the point P, you would add the translation to it. That's going to give you a result. And then you take that result and multiply it by S. See that? And that will tell you what P prime is. But understand that? It was T followed by S. Remember, the translation is an addition transformation. You're adding it. So that is if they had T followed by S. This will be the calculation. Let me show you again. You'd have to do the translation first, which is to take the point and do the translation on it. That will give you a result. They will take that result and apply the S to it. So take this result and apply the S to it, and that will be my result P prime. If I want to throw it in one step and one calculation, so I have to do inside here first. Let me just finish it. So it will be the transformation 0, 1, minus 1, 0. We're going to do this part last. And you're here going to do the P, which was 10, 12. Yeah, that is 10, 12 plus the translation of minus 3, 4. Work out in here first. So 0, 1, minus 1, 0. The S is going to now be applied to the 10 minus 3 is 7. The 12 and this 4 is 14. That is the P prime. We're applying the S now by multiplying. So it will be 0 times the 7 is 0, 1 times the 14 is 14. Then negative 1 times the 7 is negative 7. That would be your P prime. And therefore, P prime would have been 14, negative 7 if you were doing T followed by S. That's what it would be. If it was T followed by S instead. Want to go to that? All right, on the quiet so. I'm good, sure. All right. All right. All right, good. That finishes that question. Let's do the next one. It's being recorded, so if you're serious, go back and watch the recording and solidify what I've said. Work over the question and all of that. Put in some work. Put some work in. I could start January strong. Let us start January strong. An advantageous position like the chemistry teacher for whole maths. Want to start January strong. What's a young lady from me there? Wake up. Can't sleep and learn nothing. Chemistry teacher tired you out. Huh? Chemistry teacher tired you out. Come on, wake up. This question said, diagram below shows portion vectors OP and OQ. OP and OQ. Those two vectors, right? So this one is OP. This one is OQ. And you can clearly see what the coordinates are. Question says, write down in column vector form OP and OQ. Easy, because you know the points. See it here? This point P is 3, 2. 3, 2. So P is a point 3, 2. And Q is a point negative 1, 3. Q is a point negative 1, 3. So the portion vector is going to have the same values as the coordinates. So this one, OP, is going to have the same values as this point, 3, 2. When a vertical form, column vector form, 3, 2. And then OQ is minus 1, 3. So the portion vector is going to have the same values, minus 1, 3. And a column position vector format, that is it, minus 1, 3. But I write that don't look so good. Minus 1, 3. That is it. Good. Next part now says a point R is 8, 9. Express QR in this form as a column vector. I want the vector QR. So they're introducing a point R to us now. So the point R is this. It means then, can I write it here, that OR is going to have the same values, 8, 9. And therefore, the QR that I want is O times the last minus O times the first. OR minus OQ. When you have the position vectors of the points, you can find the displacement vector that way. O times the last minus O times the first. So the OR is 8, 9 minus the OQ is negative 1, 3. So the OQ right here, negative 1, 3. Work this out. This minus is a plus. 8 and 1 meant 9. Then 9 minus 3 is 6. So QR is 9, 6. Let's see if we can put this point on the diagram. If we can fit it on the diagram. It is 8, 9. Can I fit on the diagram? No, there's no space to fit on the diagram. We don't have a space to fit on the diagram. We have too small to fit it on. Because we can't put on this point on it. The scale is not wide enough for us to fit it. So that is it. But that is the vector QR, guys. All right? Next part now says, using a vectors method, show that OP is parallel to QR. If OP is parallel to QR, then 1 is a multiple of the next. You are able to say that OP is equal to some constant times QR, or vice versa. That's what it is. Show that 1 is a multiple of the next. So we have the OP, which is 3, 2, and we have the QR, which is 9, 6. Clearly, this big one is 3 times that smaller, don't it? 3 times. When it's obvious like that, we can just write it. The big one, make sure you put the right one in. The big one equals 3 times the small one, because if you multiply the one here by 3 for it to become equal to that. You see that? See that? So when you have simple numbers like that, we can just write it. The big one, QR, is equal to 3 times the small one, OR. You know, OR is OP, not OR, OP. Somebody write foolish, so not tell me. So not pay attention. OP. The big one is 3 times the small one, not OR is OP. So QR is 3 times OP. And so we have shown that by just doing that. Therefore, QR is parallel to OP, because we got this equation right here. 1 is a multiple of the next. That's what you have to do to show parallelism. Show that one vector equals a multiple of the next one. All right, that finishes that one. Next one wants us to determine the magnitude of QR. Magnitude is the length or the size of PR. We don't have the vector PR yet. Nope. We're going to have to work it out, right? We don't have the vector PR. So we're going to have to work it out and then calculate the modulus. PR. So let's go. So the vector PR for part 3, the vector PR would be equal to OR minus OP. OR is this one, 8, 9. Minus OP is this one, 3, 2. Equals 9 minus 3 is 5. Not sorry, 8 minus 3 is 5. 9 minus 2 is 7. That is PR. Therefore, the magnitude or modulus, same thing, or length, they all mean the same thing. Modulus, magnitude, length, size of PR is equal to the square root of this value squared plus that value squared. Remember, 5 squared plus 7 squared. Whatever that work out is the answer. This is the square root of 25 plus 49. 25 plus 49 is how much? 64? No, it can't be 64. 74, don't, 74. 74, that right? 74? 74
Yes,
units.
sir.
Thanks. That is it. That's it. You don't even have to work it out. That's good enough. They'll accept that. If you work this out, you're going to get some decimals. You can leave this as an exact answer. And that finishes this question, right? Oh, no. Let's retry it here, sir. Come to part B, you know, it's a nice question with so many parts. Lovely. Come to part C, you know. Part C introduces a point S, and it tells us that it is AB, so don't know the values. It says write QS as a column vector in terms of A and B, meaning A and B must be the answer. All right? So we want the vector QS. What was OQ again? Let's write them out. OQ was this one, negative 1, 3. And OS, based on this point being S, OS will have the same value as AB. Like this. It's not complicated. Therefore, QS is OS minus OQ. See? The last is S, so it's O times the last, minus the first is Q. That's O times Q. O times the last minus O times the first. This is equal to the AOS is AB minus the OQ is negative 1, 3. That's why you're working out. Careful, this minus becomes a plus. So it's A plus 1. A plus 1. And B minus 3 is B minus 3. So that is the vector QS. See, that's the vector QS right here. Want to go to that? Yeah? It says no, give that QS is equal to OP. QS is equal to OP. Calculate value of A and B. QS is equal to OP. So let's equate them. Right? They tell us now that QS is equal to OP. QS is this one. It means that A plus 1, B minus 3 is equal to OP. OP is this one, 3, 2. It means that A plus 1 is equal to 3. So the A must equal 2. Don't it? And B minus 3 is equal to 2. So it must be that the B equal 5. Don't it? So from this, it's obvious that the A is equal to 2 and the B is equal to 5. But I go to that?
Yes, sir.
Good. That's the answer. Then it says now, using a vectors method now, show that OPSQ is a parallelogram. So if OPSQ is a parallelogram, the opposite sides are equal vectors. That's what I need to show. That the opposite sides of that parallelogram are equal vectors. I'm going to sketch it so I can see clearly what the opposite sides are. I'll sketch out one OPSQ. So that means OPS must be somewhere based on Q. OP or SQ. Where's the point S again? S was, S is this point, right? S was AB. So we can put it on. Therefore, S is the point AB, 2, 5. So to see it, we can actually put it on the diagram. 2, 5. So 2, 5, this is 3, this is 4, right up here, so it's 5. So 2, 5 is all the way up here. 2, 5 is all the way up here. That's where S is. So we can sketch it out. So we have that and that. So if it's a parallelogram, then the vector here and the vector here equal. Which you already have that, you know. They told us that one. They already told us that one, right? They told us this one already. That QS is equal to OP. So we already have this pair. What is that? All right. Right, so I already have this one, that these two equal. They gave us that right here. So we have half of it already. So what we really need to show then is the other half of it. The other two sides. We need to now show that this side and this side equal. So we have to work out PS, if we don't have it yet, and show that it's equal to OQ. PS. No, we never work out PS. So we need to work out PS. Let me write it out for you. Or you prove the parallelogram. And sometimes you have to work out everything. All right? So we work it out for you. So if OPSQ is a parallel, that means parallelogram, then the opposite sides are equal vectors. The QS is equal to OP, and so these two sides, come on, Mr. Shaw, don't do that. These two sides are equal vector, which we have that already. But I told us that in the question here. See there, so QS equal OP. So what we really need to show now is these two sides are the PS equal OQ. So I want to say, and PS equals OQ. This one we know already. This one is true. They told us that. So this one we need to show. That's what we need to show now to complete the proof. We already know the part there. They told us that the part is, you can't show it, no need to show it again. This is the part we need to show. I'll show it down here now. So I want to say now, the PS is OS minus OP. I'll work out what it is and show say it actually equal to OQ. So the OQ here now, OQ is negative 1, 3. So this must work out to negative 1, 3. This must work out to negative 1, 3. So the OS is 2, 5. But the OS is 2, 5 based on this. 2, 5. Minus the OP is this. 3, 2. 3, 2. This becomes 2 minus 3 is negative 1. And 5 minus 2 is 3. And negative 1, 3. See there, negative 1, 3 is actually OQ. So the PS is equal to that. So we can say IE PS is in fact equal to OQ. All right, which is now true. So the two things, two sides, two opposite vectors are equal. Two pairs of equal opposite vectors. And therefore, we have a parallelogram in fact. Therefore, it is true that OPSQ is a parallelogram. That is it. And I like to ask the proof of parallelogram, guys. Show that you have a parallelogram, to show that the opposite sides of the opposite sides of the parallelogram are equal vectors. That's all you need to do. Show that the opposite sides of the parallelogram are equal vectors. That's all you need to do to prove that you have a parallelogram. Proving a parallelogram is something that CSEC like to set in questions. That finishes that one. Very good. Online, very good.
Yes, sir.
Beautiful.
Yes, sir.
Go and do the question them again over. Read them over again. More maths equals better math. I'm going to share the video later. All right. So I gave you all a paper to do. Nice paper. Let me see if I can find it. It was January 2011 or June 2011. Which one? January 2011. All right, let me see if I can find it inside here. So let me see if I can find it in here. January 2011. January 2011. I do have it in here. I don't have it inside here. Really. Let's look somewhere else for it. Let's look for it somewhere else. Let's find it. There you go. All right. All right. So I gave you a number of questions on this paper to do. But I'm not going to work from the front. I'm going to work from the back. Because the questions around there are much nicer. Much nicer questions. All right. Yeah. So I'm going to work from number 11. I'm going to work from number 11. And then we're going to see how do as many of them. I gave you a good A. It's so much questions on the paper they're going to do. You know what I mean? Let me say which far in the syllabus, you know? If I can give you so many questions, the 11 questions on the paper, and I was able to give you so many of them to do because these are topics that you already covered. The 1 and 2, when I will teach them the like so, you know, 1 and 2, we just do those by example, especially number 1. We really like our class when we teach that. We just practice it because basic stuff, like the fractions and consumer arithmetic and those things. We learn those by example inside here. In a have a class, we put a projector and notes and all that. I don't need it. We learn by example, just practice it. And our class will go through the fundamentals and the basics here. But most of it we do by example, right? Because consumer arithmetic is living mathematics, you know, mathematics that you live and do every day. So it's not hard to understand. Because everybody spend money, and you all know about spending money and getting discount and getting interest, paying interest and pay tax and all them something there. You understand? Profit and selling and buying profit and loss. We live that every day, so that's not hard to learn. All right, let us go. Starting at number 11 on this January 2011 paper. The mathematics was nicer than now. It says, under the matrix transformation, this one, the point V and W are mapped onto V prime and W prime. So see it here? This point is mapped onto that point, and this point is mapped onto that point. I don't want us to work on the value for A, B, and C, and D. So if you notice the difference, we just do one like that a while ago, you know. But they only wanted to work out 2 of the values, X and Y. See the difference? Now you have to work out all 4 values. So we're talking now. So what happened? You don't really need to do all the calculation. You can just work it smart. Because look at what is that mean now. It's really the same values come back over here now. 5 and the 3 and negative, right? So you know that the values involved here are 0, 1, and negative 1, right? See that? Same thing happening here. This come to this. Again, 7, 2 becomes 2 and negative 7. So again, the values in the matrix must be 0, 1, and negative 1. All right? So you know it's one of our matrices we're working on. All right? And the same way the values change for this pair is the same way they change on this pair. So like, for example, the value inside here comes to the front. The value inside here comes to the front. And the first value goes to the back and change sign. First value goes to the back and change sign. All right? So we'll see that. But let me set it up for you. I don't need to use both points. I can use 1 point. Remember, the values are 0, 1, negative 1. So let's be smart about it. All right? So A, what we know from these, because of those values, is one of our normal matrices. This is one of our regular matrices. So the A, B, C, and D are going to be equal to values from 0, 1, and -1 for sure. Know that, right? So I'm going to set it up. The matrix A, B, C, D times the matrix for V, for example, which is 3, 5, is going to be equal to the matrix for V prime, which is 5, -3. It means then equality of matrices method can be applied. So this row times this column is equal to this 5. So we can set that up. Remember, I know these values can only be 1, -1, or -1. And the matrices always have the zeros on the diagonal here, or the zeros on the diagonal here. So you know, for example, that one of these values is 0, don't it? And one of these values is 0, for sure. You get me? All right. So we know that this row times this column equal to 5. Let's set it up and be smart about it. So we know that the AB times the 3, 5 is equal to this 5 right here. That's this row times this column equals that 5. Better go to that. Better go to that, right? So if we were to expand it out, it will be A times 3, which is 3A, plus B times 5 is 5B. That's all equal to 5. So based on this now, one of these values must be a 0, and the other one has to be a 1 or a -1. Which of them have to be 0 for the other one to be 1 or -1 from these two? By observation, these two.
The 3, sir.
Is the A or the B me at all?
The A, sir,
or the
A.
B? Huh?
The A, sir.
A has to be 0, don't it? But
Yes,
you can see that if the A is 0, then you have this. The B becomes 1, right? Look, if you put the B equals 0, you're going to have 3A equal 5, and the A not going to be 1 or -1. You see that? So you choose them that way. It's simple. We're not going to complicate it. So the A is 0, and the B becomes 1. See that? Simple as that.
Yes,
But go to
sir.
that? Good. Keep it
Yes.
simple. Then we're doing the next pair. Nice and easy. The next pair is this row times the 1 column equal to -3. Let me do it in red. So this row times the 1 column equals -3. So setting that up again. Let's set it up here now. So the second one is that the CD times the 3, 5 equals -3. So you know that this C times this 3 is 3C, and then this D times this 5 is 5D, and that's all equal to -3. One of these values must be 0, and the other one will be 1 or -1. So based on these two now, again, by observation, it is not complicated. You work with simple numbers, 0, 1, and -1. Which of these must be 0 for the other one to be 1 or -1? The D has to be 0. And the D is 0 is gone. And if the 3C equal -1, then what is the C? 3C equal -3, what is the C? -1. Simple. Keep it simple, not complicating it. So in this case, the C equal -1 and the D equals 0. See that? And we want to know what matrix it is. I'm going to write out the matrix now. So that matrix M equals A. The A is what? The A is 0. B, what is B? The B is 1. C, the C is what? -1. D, the D is what? 0. Same matrix we got again. That's a 90-degree clockwise rotation about the origin, if they ask you for it. You have to know the matrix is on site. That's a 90-degree clockwise rotation about the origin. That matrix right here. We're not going to study them and know them. The question is a bit easy. So we have determined the values for A, B, and C. A, B, C, and D in the first part. Look here now. Next part now says, state the coordinates of Z, X, Y, map onto Z prime under the transformation M. Now this no need no calculation, you know. It's no need a calculation. Just need to observe. Look. So it's as if you want to reverse one of these, and look how one of these reverse. So what happens? This -7 go to the front and change sign, don't it? See that? So this 1 must go to the front and change sign, become a -1. Becomes a -1. Let me write it this way. I'm just showing you the easy way to do it. That's the beauty about transformation. Anything that happens to one point happens to all other points. So if you look at the -7 on the image here, it is coming from a 7 in the X position. So this 1 in the Y position on the image is going to become the X value with the opposite sign of 1, which is a -1. Nobody can see that? Nobody can see that? And this value here, that is the X value on the image, is coming from a Y value with the same value, don't it? So it's simple. This 5 is coming from a Y value of 5 right here. This 5. That's a 5. So the matrix is -1, 5. But I can see that. Not complicated. Anyway, the values change by M up here, it's the same way going to change on this. Going this way or going that way. It's the same change you're going to have. I'm not going to do the mathematics harder than it has to. I told in the class that anything the transformation does to one point, it does it to all the other points. That was one on the first slide that I gave you when we did the transformation. I said to you, anything that the transformation does to one point, it's doing the same thing to all other points. So all you need to do is look what the transformation does to one point already and apply the same change to the other points. Apply the same change to the other points. So this has to be the answer right here. -1, 5. And if you want to check it by the other way to see if it is correct, you can do that. Look, let me zoom it up for you. Check it by the other way. So I'm saying the answer is 1, 5. The original image of Z is 1, 5. Look at the W. So the value that is in front, the Y, the 7, it goes and become the -Y value. It goes to become the Y value and it changes sign. So this -1, which is in the X position, goes to become the Y value and change sign to a +1. So this -1 is correct. But understand that. And then let's look what happens to a Y value. This Y value goes and becomes the X value on the image. And there's no change in sign. So see here, this Y value goes and becomes the X value on the image and change sign. So this must be the correct answer. This has to be the correct answer. But I'm saying to get what these values were, you could look at the change from this back to that and apply the change the same way in terms of the positioning of the values and the change in sign of the values. We don't need to calculate on this question. It's like a 3 marks question. Apply the same change to the points. But I go to that. Now do it another way. No. That is it. Not gonna do it in a other way. Any way other than this, it's more work. So Z is a point -1, 5. That is it. Z is a point -1, 5. Just like that. By that reasoning. Then you know what I'm saying? Now, describe transformation M fully. So it's good to know the matrix. M works out to be 0, 1, -1, 0. That's what we got for M. Right? 0, 1, -1, 0. See it there? What's the best way to describe this fully by just knowing the matrix? Just know it. Rather than go trying to figure it out. Some people, when they do the exam here, say, when they do this exam, to figure out what M is, you know what they did? They draw one graph and then plot the whole of them points upon it to see what happened. Foolishness and waste of time is only 2 marks for that. Them draw a graph, put on the whole of them points so they could see what happened because they did not know this matrix in their head. What a sense. Just learn the matrix in your head. You want to get one in the exam the easiest way possible. You want to finish the exam, get your marks easy, go about the business. Make other people stay upon a question and spend 10 minutes on it. You need to spend 5 seconds on it by just knowing the matrix. Come on, man, and you must have enough proof now of why I'm telling you to learn these matrices. You see them in the questions and asking you to describe them. Where the sense go in the exam, go waste time and try to figure it out when you can just know it. The more things you know, the better. The more things you know, the better. The more things you know, the better. Stop talking. Stop talking. M is 90 degrees clockwise rotation. You can't stop this. If you stop this, you're going to lose a mark. You have to say about the origin. You have to say the center. About the origin. Rotation has 3 components. The name of rotation, you give the name first. They give the 3 components of rotation. Angle, direction right here, so, and center right there, so. You have to state all 3 in your description. You give the name, which is rotation, the name of the transformation, and transformation, rotation, transformation has 3 components. Angle, direction, and center. You have to state everything, otherwise you're going to lose marks. Remember, clockwise rotation is negative rotation. So instead of saying clockwise rotation, you could say M is a negative 90 degree rotation about the origin. This negative is giving you the direction. If I put a negative here, you're saying it's clockwise. Clockwise rotation is negative rotation. Anti-clockwise rotation is positive. I tell you every day, you know. Because I don't know what's coming in the exam paper, so I'm going to remind you. Especially because I know that they don't set that very often in the exam. The positive and negative for rotation. Clockwise rotation is negative. Anti-clockwise rotation is positive. If it's 1 mark we need to know that, we want to remember it. We want to know it and remember. Every mark on the exam paper we want to get. Every single mark on the exam paper. So once they will possibly set it, we want to make sure so we know it. Clockwise rotation is negative. Anti-clockwise rotation is positive. So you could have described it this way. But let's work with the clockwise and anti-clockwise still. But you could get a question that says positive or negative. I'm telling you, you're going to see it on some past papers. Not some, and a very few past papers. Like maybe 1 out of 100. You might see the positive, negative business. I'm telling you. And when CSEC set that one, enough people get it wrong. Because them just guess. They don't know. They don't know. They see the positive and the negative and they don't know. Positive is anti-clockwise. Negative is clockwise. Make it stick. It's going to be valid 1 mark in the exam. And it's going to be valid 1 mark. I want you to get that 1 mark. It is set. All right. That is that. Then we'll come to this vectors down here. Better go online. I always forget the people online, you know. Yeah. Online, better go. We'll have 11 people. All right. Let's continue. Let's continue. Vectors now. Fun question. Vectors. But this one is only values. So it gives us OP and OR are position vectors, and it tells us that P is this point and PR is that vector. Easy. So they want us to write OP and OR. Question look like we do it already, so. Question look familiar. No problem. More maths equals better maths every time. So let's do it again. A lot of the questions we do, we're going to do them again multiple times. I'm telling you from now. All these past papers I'm doing, all these questions I'm working on, you're going to have to do them on the exam condition. All of them. All of these papers I'm working out, you're going to have to do with them. The whole paper in 2 hours, 40 minutes. All of them, you're going to have to do. I'm telling you from now. All right. So they give us the point P, which is 27. It means that OP is 27. No calculation needed when you know the point. Then they give us the vector PR is 4, -3. And from this, they wanted to extract OR. A nice way to do it is to pull it up, split it up into position vectors. That's one nice way to do it and make OR the subject. Pull it up into position vectors. So since they give me this vector equation right here, I'm going to split this side into position vectors. That's a nice skill to have. So pull up this side on the vector, you write as OR minus OP and put it back equal to 4, -3. And see, you know the OP already. The OP is this. And so you can find the unknown, which is OR. Transpose the OP over that side and make it plus. You get the OR is equal to 4, -3 plus the OP. I'm not going to put the values of the OP beside it. The OP is 27, right? OP is 27. So that's what they're working on for the OR. Nice and easy. So the OR then becomes equal to 4 and 2 is 6. Minus 3 and 7. Same as 7 minus 3 is 4. That is the OR. Nice and easy. Show another way you could do it now. More maths equals better maths. Look now. You have OP is 27, right? And you have PR is 4, 3. Okay. So we have those two vectors now. This one start at O. Remember, you're trying to find OR right now. So you want to see how you can combine those two vectors to find the OR. This one start at O and go to P. And I want to go from P to R. So it means that you can use these two and go from O to R and use P as your stopping point in the middle. See that? You can use P as your stopping point. P like downtown. So like you want to go from O to R, you go P first. The bus can go P first at the station. And then from the station, they go to R. So you can set up like that. And say, all right, to go from O to R, I can go from O to P first. And then, plus means and then, you go from P to R. So you see those two vectors give you take from O to R. The OP is 27 and the PR is 4, 3. So it works out to be 6, 4, just the same that we got a while ago. 6, 4, see there? Same 6, 4. So this method up here, we use the one where we split the vector equation and make OR the subject. That's one way to do it. Or we can just use the displacement vector.
That's not supposed to be a -3.
Huh?
That's supposed to be a negative.
-3. That's what a -3? It's 4. Oh, it's 4 -3. Hold on. So make a mistake up today. So why not work out? It's 7 minus 3. Oh, sorry, 7 minus 3. Okay, 7 minus 3. All right. So I have the same answer. 4, 3. 7 minus 3. All right, well, that's it. But that shows you how you could get it. It's -3. But that shows you how you could get it. Just the same. Same work. I left out the negative, but it's the same work. But that is it. All right. So we finish these two parts right here on the question. The next part now introduce the point S. So if I'm going to tell you that this is the point S, then automatically OS is 14, -2. Question like we did already. So find RS and then prove that PRS are coordinated. I want us to find RS. So since we know OR and we know OS, we can find RS. Nice and easy. Let's do it down here. So OR, we just worked it out a while ago. It was what? 6, 4? 6, 4. Is 6, 4. And we have OS is 14, -2. Therefore, Rs is O times the last minus O times the first. OS minus OR. O times the first minus O times the last minus O times the first. That's 14 negative 2 minus 6, 4. So it's 14 minus 6. 14 minus 6 is how much? 8. And then minus 2 and minus 4 is negative 6. So that is the vector RS. So I've completed this part. Then show that PRS are collinear. PR and S are collinear. So remember, to show that PR and S are collinear, you need two vectors between those 3 points. You need two vectors between those 3 points, and one must be parallel to the next one, meaning one is a multiple of the next, and there must be a common point. Let's set it up. So we're doing PR and S. PR and S. Collinear, testing collinearity on these 3 points. So you need two vectors between these 3 points. Look if you have them yet. Do we have them yet? Yes, we have PR. They gave us PR. So we have one of them between these 2 points, PR. So PR is 4, negative 3. You need another one with the S in it. But those ask us for RS, don't it? Theta RS. So another one between those 2 points, RS. And RS is 8, negative 6. Now that's obvious already. This big one is 2 times that small one. If you don't know, it will follow the process. Multiply the small one up to make it equal the large one. So you have to multiply this one by a 2 to make it equal that one, and then equate. But with simple numbers like these, it gets obvious that the big one RS. So you can say, therefore, the big one RS is 2 times the small one. So this is 8, 6, and this is 4, 4, 3 with a negative, right? So this is 2 times the small one. So the big one is 2 times the small one. This means that they are parallel. So two things that mean in this equation here. Let's mark the common point as well. Common point is the R. So two things for collinearity happening here. One is that they are parallel. RS is parallel to PR. That's the first thing you must have for collinearity, for collinear points. The second thing is that there must be a common point. We should have R as a common point. R is a common point. And because these two things happen, we can draw the conclusion that the points are collinear. P, R, and S are collinear. That is it. Very good. Very good. Soft with a capital T. Soft with a capital T. All right. That finishes that one. Which one did I give it to though? That was number, I gave it number 9, don't it? Yeah, we're gonna do this topic next, right? We're gonna do this topic next. And these things. We're gonna do these things next. Well, this next, this one first. Bearings and so on. And then after that, we're gonna do circles. So these come in early in January. These come in early in January. Early in January, we'll be able to do this question. After 2 weeks in January, we should be able to do the whole of this question. Or 3 weeks in January. All right, number 9 was the functions question. Let's go. Number 9 is a functions question. Let me say the time. I don't want to be too long enough. So start the class about 5:30, don't it? Start late. Yes. No, start class 5:30. But I'm going to 2 hours. We have finished this about 7, after 7. Come, I can do this question right here. Revise it. All right. So this question gives us these two functions, right? Gives us these two functions. F of x is 2x minus 7 over x g of x is the square root of x plus 3. First part one, f of 5. Meaning you're going to put 5 in the f function right there. So we're talking now. F of 5, meaning putting 5 in the f function. It becomes 2 times 5 minus 7 over 5. Now this is 10 minus 7. 10 minus 7 is 3 over 5. That is it. Next part wants f to the minus 1. Part 2, a wants f to the minus 1, the inverse of this function. No, that's a rational function, right? Start by saying f equals 2x minus 7 over x. We're going to inverse it. The f, which is range on the function, becomes domain on the inverse. These x's are domain on the function right now. They're going to become range on the inverse. Range on the inverse is f to the minus 1. So it becomes 2 f to the minus 1 minus 7 over f to the minus 1. I will now need to transpose to make f to the minus 1 a subject. First thing is to multiply this across here. Spread it out and separate all the terms. So it becomes f to the minus 1 times x. So it becomes x f to the minus 1 equals 2f to the minus 1 minus 7. Take this over here and put with that one. It becomes x f to the minus 1 minus 2f to the minus 1 equals negative 7. But go to that. And then factorize all the f to the minus 1 out of these two terms. So it becomes f to the minus 1 into, out of this we get the x, out of this we get a minus 2. That equals negative 7. You take x minus 2 and divide it on this side. Shortcut. So f to the minus 1 equals negative 7 over x minus 2. That is f to the minus 1 of x. That is it. Finishes that one. Next part wants us to do g of f. G of f. So remember, let's set up right here. So let's set up right here. So this is g of f. It means f into g. That's how we construct it. Put the inner function into the outer function. This is the f1. This over here is the f1. Take all of the f and bring it and put it into the g where the x is right here. And everything else stays where it is. That's how I formed it. That's how you put f into g. So we do that construction, we're going to get it. G of f of x is going to be based on this construction that I've set up over here. Put by the square root. Where the x is, put all of f there. 2x minus 7 over x. That's where the x was a while ago. Plus 7 beside it. That is it. I don't need to bracket this enough. But I can just bracket it still. Don't really matter whether I bracket it or not. But that is it. That's where the x was a while ago. In the g. I will replace it with all of the f. But I go to that?
Yes, sir.
That is it. All right. Then we'll come to part B, which is our quadratics. First part was our simple functions. Now we'll come to part B now, which is our quadratics. So let's set up this time. They don't set it the same way all the time. They give us this expression and they want us to write it in that form, which is to complete the square. Don't try to set up any differently. Do it the same way all the time, so you move more smoothly, more quickly through doing the question. When you do it the same way all the time. All right? So you're going to complete the square for that one. All right. So let me give this expression a name so we can reference it. All right? I was looking if they call it anything else down here, but they didn't. I'm just going to call it y for simplicity. So I'm going to say let y be equal to 1 minus 6x minus x squared. Let's write it in the standard form. Put the x term in front. You have to carry the negative with it, you know. So it's minus x squared, the x term next, or the x squared term in front. Minus 6x, and then this positive 1 plus 1. So in this standard form, The a is -1. The coefficient of the x squared is by -1. Like you have a -1 there. -1. The b is the coefficient of the x, which is at -6. So the b is -6. The c is this constant 1. The c equals 1. So those are my a, b, and c. For this, for completing the square, I'm going to use a normal method that we use. I'm going to write this as, let's do it in purple. Write this as y equals a into x minus xt squared plus yt. So xt and yt are the coordinates at the turning point. That's what the t stands for. Xt can be calculated from these values with the formula. Xt is minus b over 2a equals minus, that is this minus right now. Then the b is actually -6, so it becomes a minus -6 over 2a, the a is -1. This becomes a positive 6 over a -2. Positive 6 over -2 is -3. Then you can find yt two ways now. You can take the xt value and substitute it in the function right there where the x is. Or work out yt that way. Or we can use a formula to do it. We can use a formula which is 4ac minus b squared all over 4a to do it. All right, whichever method you're going to get the same answer. So this works out to be what? Let me do it here. The 4 times a, the a is -1. Times c, the c is this 1 right here. Minus, this is this minus. Not squaring, stays a minus. You're squaring the b, which is a -6. You're squaring the entire -6, going to become a positive 36. All over 4 times a, where the a is again is this -1. Let's consolidate the values now. That's 4 times -1 times 1 becomes a -4 right here. This stays a minus, and this becomes a 36. Divided by, this becomes a -4. So yt equals, that's a -40 over -4. The negatives cancel, and 40 over 4 is 10. So yt is 10. But let you know the x and yt, you can plug them in this one. And so this expression up here becomes y equals, the a is -1. -1 bracket x minus this -3. Minus minus becomes a +3. Don't forget your square. And then you're adding yt, where yt is 10 plus 10. But go to that. And if you want to make it look like this that they gave us, you can put this as a k in front. Right? And so it becomes y equals 10 minus 1 into x plus 3 squared, if you want to make it look like that, which it now does. But go to that. That is it. All right. Remember, I could have found the yt as well by putting the -3 in the function right there. Supposed to get 10 same way. Let's do it over here. More math equals better maths. So we have y equals -x squared minus 6 times x plus 1. We put in the -3 in it, right? So the yt would be minus a -3 squared minus 6 times -3 plus 1. Now this becomes a 9. This negative don't square, so it stays negative. So it's minus 9. This minus is a plus 18 plus 1. That becomes 19 minus 9 is 10. So you see, you can get the yt value from the xt value in the original function as well. All right? So in the exam, you choose a path of least resistance. Quickest way, easiest way to do the question. Usually when xt value works out to be a whole number like it is here, I prefer to use this method by plugging that value in the original function. All right, that's what I prefer to do. All right, so that finishes that part of the question. The next part down here says we have to state the maximum value. The maximum value is the YT value. Which is 10. Simple as that. Next part says the equation of axis of symmetry. Equation of axis of symmetry is x equal whatever the xt value is. Xt value is -3. So the axis of symmetry is x equal -3. This is the answer. Axis of symmetry. X equal whatever the xt value is. Easy. All right. Next part says determine the root of this equation, giving an answer to 2 decimal places. I'm going to use this to do it this time. Because sometimes CSEC forces you to use this vertex form to solve the equation. All right? I'm going to do it this time for you. Rather than use the quadratic formula. You see, once I tell you something like this, giving an answer to 2 decimal places, it is because you're not going to be factorizing it to do it. You're not going to be using the factorization method. You're going to use the quadratic formula, right? So let's look at it now. So they gave us this thing to solve. 1 minus 6x minus x squared equals 0. But this expression, what we just completed the square for. This in the vertex form, this is a standard form. In the vertex form, it is 10 minus 1 bracket x plus 3 squared. Same thing obvious, right there. I don't need this one right here now. I don't need it. So I'm going to take it off. Put this as equals 0. I'm trying to make this x a subject. All right. I'm going to take all of this and transpose on that side, make it positive first. I'm going to get 10 equals x plus 3 squared. Then to get out of this square, I'm going to square it both sides, but this is the kicker. You have to remember that when you calculate square root, it can be plus or minus. You cannot forget. That's where the plus or minus comes from in the formula, in the quadratic formula, square root part. So we're going to get plus or minus the square root of 10 equals x plus 3. Because the square root is gone, the square root is gone, square root both sides. Then to leave x as a sub, we have transpose this 3 and make it negative. So the x is going to be equal to -3 plus or minus the square root of 10. I'm going to get one answer with the plus and another answer with the minus. All right, so let's get the calculator. We need to write it over here. So it's -3 plus or minus the square root of 10. That's what we're doing. Let me do it to the calculator over here now. Come up, come up, come up. We're not going on. All right. So it's -3 plus square root of 10. So one answer is 1 decimal place, 2 decimal places, 2 decimal places I want. So it's 1/6. And with the minus changes plus to a minus, I get -6.16. So those are the 2 x values. Those are the 2 x values there. So getting x equals -6.16 or x equals 0.16. Those are the values. Want to go to that? So that's why you can do it sometime from the vertex form. Just transpose everything away to make X a subject. But remember, the part where square root, you have to go plus or minus. Has to be plus or minus. That finishes that. Not even 7 o'clock yet. So that question is done. I want us to do transformation question before we leave. I want us to do transformation question before we leave. All right. I gave you number 7 to do, don't? I gave you number 7, right? All right, number 7. No one go home. One go to idle. Number 7. Pay attention. I bet you in the class don't know this to stand up for 1 hour idle and waste time. So I can't take you now. Yeah, you know that hurt me all the time. I'm done class early. I'm just outside of chat. That's how much work till the parents come. No, I studied nothing. All right, let's go. All right, this transformation question. Let's look at it. It says, the diagram below shows triangle RST, which is this one, and its image R prime, S prime, T prime after a transformation. So this transform to that. Write down the coordinates of R and R prime. This is R. That is 2, 4, don't it? So R is 2, 4. And R prime. R prime is this. That is 2, 0, right? R prime is just 2, 0. Next part says, describe complete transformation which maps this to that. What is it? What is it? What transformation maps this to this? Cannot just say reflection. You have to state the mirror line next to reflection. Reflection line y equals 2. Once it's a reflection, you have to state the mirror line. All right, let's use a process of elimination for those who don't know. So it's not a translation. Because with a translation, they would look exactly the same. They clearly don't look the same. Some kind of turning like it take place. Or some kind of flip or some kind of orientation change. They're not the same. So a translation, they would look exactly the same, just in a different position. It's not an enlargement, because if it was an enlargement, one would clearly be larger than the next one. So it's not an enlargement. So it's either a reflection or a rotation. Now, a lot of pros are going to look at it and think it's a rotation. Think that this rotate go wrong, so you know. A lot of pros are going to think it's a rotation. Think that this rotate somewhat go wrong, so. But rotation and reflection often look alike. To decipher and break the confusion and to make a determination of which one it is, all you need to do is check the orientation. If the orientation is reversed, then you know you have a reflection. If the orientation is the same, then you know it's a rotation. Because we eliminate translation already, and we eliminate enlargement. So the only 2 left on your syllabus. There are other transformations in them. I'm talking about the ones on your syllabus. Enlargement, translation, reflection, rotation. Talking about the single transformation. We're not talking about the compound transformation. This one is a single transformation. See, a transformation, one transformation. So as I said, rotation and reflection can often look alike and can be confusing and not sure. The way to be sure is to check the orientation. If the orientation is reversed, you have a reflection. Reflection in a line will always reverse the orientation. Orientation is basically how the letters go around the object alphabetically. So if them don't give enough letters on it, you letter them to corresponding points and check the orientation. So T, S, and R. P, Q, R, S, T. R, S, T in alphabetical order is this way. Up here, so don't it? Now the pen going. All right? It's this way. Clockwise, right? R, S, T on this one is the opposite orientation, opposite way. So once the orientation is reversed from clockwise to anti-clockwise, you know you have a reflection in a line. The mirror line will always be equidistant between the points. So the mirror line is halfway between the R and the R prime. The mirror line is somewhere here. This is halfway. Halfway between the T and the T prime. Again, it's here. So the mirror line is this. That's the mirror line. Halfway between corresponding points. That line is a horizontal line. So it's Y equals a number. Don't give it away. The x-axis, remember, is Y equals 0. So horizontal lines like the like the x-axis is Y equals a number. This one passes through 2, so it's Y equals 2. So we have a reflection in the line Y equals 2. All right? So let's say that. So R is mapped onto the first one. The object is mapped onto the image by a reflection line Y equals 2. So for part 2, we're going to say this. RST is mapped onto R prime, S prime, T prime by a reflection only has one component, which is the mirror line. State the mirror line. By a reflection in the line Y equals 2. Reflection has one component, which is the mirror line. Give them the equation of the mirror line. I'll tell them what the mirror line is. Better go to that. All right.
Yes, sir.
Beautiful. Next part says, all right. Sugar part now. Pen going bad. Next part says, RST undergoes an enlargement, center 0.7, scale factor of 2. And I want us to, on the answer sheet, draw that image triangle, R double prime, S double prime, T double prime. See here? I want to perform this enlargement, or enlargement with these components on the triangle and name it R double prime, S double prime, T double prime. So remember, this is not the center of the enlargement, so we can't use the enlargement matrix. This is not the origin. The center of the enlargement here is not the origin. So we can't use the matrix 2002. We're going to have to construct it. The key thing to remember about enlargement and the scale factor is that the scale factor also affects the distance from the center of the enlargement. So since the scale factor is 2, the points are going to be pushed twice the distance from the center of the enlargement. And this is the positive scale factor. So it's pushing it away from the center. It's not going on the opposite side of the center. That's all you need to do. The sides are going to end up doubling now. But the best way to construct it is to know that the 2 is going to double the distance from the center of the enlargement. So let's put on the center of the enlargement on the diagram first, which is 0.7. 0.7 is right here. Let me zoom it up for you. Let me close this out and do it here so you can see everything. So 0.7 is this point right here. So put in the center of the enlargement there. Then each point must go on a scale factor of 2. Enlargement scale factor affects the size on the actual object. It affects the size on the object, but it also affects the distance from the center, those distances, which is the best way to construct the enlargement by doubling those distances because the scale factor is 2. If the scale factor was 3, you would have tripled the distance. If the scale factor was 4, you multiply the distances by 4. All right? The scale factor was negative, it will go the other way. It will go this way on this side of the center. So if it was -2, for example, if it was -2, Whatever this distance is, they put it double that distance on this side, opposite. The scale factor was -2. From this distance, you are double that distance on this side, opposite side, double the distance. Whatever this distance, you double it over here. On the opposite side of the center, the scale factor was negative. Since it is positive, you're doubling it in the same direction. Doubling it down so. All right, let's look at our doubling. Let's go. Take it step by step. We're doing the enlargement on this one. Pay attention. We're going to finish the class with this, right? So make it stick. Make it stick. We don't know what's coming on the exam. So this distance to S has to be doubled to get to the image, don't? That distance is 3 units. 1, 2, 3. So it's going to go to 6 units, right? So they extend this out to 6 units, 3 more. So the distance from here is doubled to that. So the image of that one is right here. That's where S double prime is. But to go to that, it's an easy one. Straightforward. Let's do T. This distance down to T is doubled. If you want to measure the rule and extend it out, no problem. That distance is doubled. So since it's not horizontal like this, we can just count the squares. What you can do with this distance is break it down into vertical and horizontal displacement. And then you double this vertical and horizontal displacement to double the distance. So this was 2 down and 1, 2, 3, 4, 5 across. So it's going to go 4 down. 4 down. 1, 2, 3, 4, 10 across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across to here. If you extend this line, you'll see it. Extend this construction line, you'll see it. See there? So this is where that point is going. T double prime. This distance is doubled out to there. I'll scale factor of 2. So a scale factor of 3, that triple the distance. But I go to that. So that is where T double prime is, right out here. They were doing for R next. This distance out to R from the center is doubled again. So if you want, you can measure it and double it down to there, so. Or you can again break down that distance into the component that you can count. How many units down here and across? This is 1, 2, 3 units down and 2 across. So you double that down to 6 down, 4 across. 1, 2, 3, 4, 5, 6, and 4 across. 1, 2, 3, 4. That's where it is coming. And so this distance is doubled. This distance is doubled down to there. So right here is where the R double prime is. Take these off now. So those are my 3 image points. Just draw them on in blue. So you're going to join them in blue. These are my 3 image points of the enlargement. So we're going to join them like this. That blue triangle is your image of the enlargement. But understand that? I want to go and do it by yourself if you didn't do it. That is it. The red lines are just a construction line. Let me take them off. The red lines are just the construction lines. All right? That's what the red lines are. Put them in back. Construction line out to here. And largest one down to there. The largest one down to there. That is it. Don't need them. But I sure they understand. Go and do it over by yourself. But the foolishness. All right. That's the image of the enlargement. I think this question asks us for some area now. Let me see. So we'll do this first part here. Just to construct it. All right. See it now. Given that the area of the image triangle is 4 square units, calculate the image of the double prime. State two geometric relationship between them. Now we're about a part of 2 months because I want to do plain and solid geometry here. All right? But we have to remember the relationship of area and this. It tells that the area of the images object is 4. This is where you have to remember. Area of the image of an enlargement is k squared times the area of the object. The k is 2, you know the k is 2, and the area of the object is 4. All right? You have to remember that this, guys. Plenty of people go and just do k times, you know. Because the scale factor is 2. Plenty of people go and say 2 times 4. Multiply the scale factor by thing. Don't worry for area. You multiply the scale factor for distance. You multiply the square of the scale factor for area. You have to absolutely remember this. K squared. Area of the image is k squared times area of the object. So this calculation becomes equal to 2 squared. The scale factor is 2. Remember? 2. 2 squared times the area of the object is 4. That becomes 16 square units. 16 square units. Give back to them when I give it to you. So that's size 16 square. Plenty people put 8, which is wrong. But I go to that. The last part asking us for 2 geometric relationship. The geometric relationship have to do with like area, parallelism, if the angles are the same, the length of the sides, stuff like that, perimeter. So the distance on the object is doubled, so the perimeter will be twice, right? Perimeter of the big, this one is twice that one. The 3 angles are the same, 2 geometric relationship. They have the same triangles, so they are similar triangles. We don't do that topic yet, but they are similar triangles because the 3 angles and the 2 triangles are the same. Even though the dimensions are different, the 2 angles are the same. The 3 angles are the same. So this angle up here is the same as this one. This one is the same as that one. And this one is the same as that one. So they are similar triangles, they have the same 3 angles. That's one geometric property. Another geometric property is that the perimeter of this one, or the perimeter of the big one, is twice the perimeter of the small one, right? But the area of the big one is 4 times the area of the small. You could tell them that as well. The area of the big one, the double prime one, is 4 times the area of the small one. Because I say it was 4 to 16. The 2 squared became 4 times. So you could tell them stuff like that. All right. So those are some geometric properties, a geometric relationship. Let's start with some of them. So they have the same 3 angles. That's one. So because they have the same 3 angles, they are similar triangles. But in terms of dimensions, the sides on the big one are twice as long as the sides on the small one. Because perimeter is the addition of your sides, then the perimeter of the big one is twice the perimeter of a small one. I could tell them that as well. Talking about area though, it is a square relationship in terms of the scale factor. So the area of the big one is 4 times the area of the small one. If you want to talk about area, you could tell them that. Get me? So those are some geometric properties you could have given. You could have also said they have the 3 equal corresponding angles, 3 equal angles. All right, guys, I'm going to end it there. I'm not going to let you suffer anymore. More math equal better. I'm not supposed to have suffer, you know. This is fun, you know. I don't know, you guys don't see the fun in this, you know. All right, everybody online. So the next class, which is Saturday, we're going to continue on this paper. And I'm going to send another paper in the group for you to do, okay? More math equals better math. I'm going to send another paper in the group for you to do by Saturday. Is that all right? I remember who was it. And I know the names them now a little bit. All right. All right, bye everybody. Bye online students. Remember, when I send the questions in the group, make sure you do them, please. Bye everybody. All right. I'm gonna end it now. You guys swam today? Swam today? Huh? Oh, and on Tuesday. Okay, okay. Huh? I won't have class on the Wednesday because it's Christmas Day. I give it that day. But we're having classes the other. We're having class Sunday. And we're gonna have class Saturday. I'll let you know. I'll send it to the group. Where we don't have class, I'll send the work just the same, okay? All right. I'm gonna send a multiple choice in the group as well from